All right, welcome to the Friday Transportation Seminar at Portland State University. Usually I get to introduce the speaker, but today I am the speaker. So my name is Chris Monsere. I'm a faculty member in Civil and Environmental Engineering, and I'm going to be talking to you today about some research that my colleagues and I completed last spring on studying the safety effectiveness of pedestrian crossing enhancements in Oregon. So just as a little background about why we want to look at the safety of pedestrian crossings. The pink line is total reported pedestrian crashes. These are in Oregon from 2004 to 2015. And you can see the steady increase in the number of reported pedestrian crashes. That's all injuries. So about in 2015, which is the last year that data was available from the Oregon DOT, about 850 pedestrian crashes in 1 year. The blue line is the fatal crashes, where those crashes resulted in a fatality. In 2015, there were 70 fatal pedestrian crashes in Oregon. And both those lines, if you look at the longer-term trend, has been steadily increasing. A little bit closer to home, if you look in the Portland metro area, and generally in any urban area, pedestrian fatalities tend to be close to 40 or 50% of the total fatalities in an urban area. And that's because there are more people walking and biking in urban areas than they are in rural areas. This is data from Portland's Vision Zero program. You can see the bar chart over here that's on the left side here shows 15 pedestrian fatalities in 2014 and 38 serious injuries. That's roughly half. It's roughly half of the fatalities in Portland in 2014. No, this is just let's see. This is just people walking. There was one in 2014. I think there was one bicycle fatality. So bicycles, when you look at the motor vehicle fatality data, it's there's always fewer bicycle fatalities than there are pedestrian fatalities. So just a quick, if somebody wants to take a look at that map, and the orange and yellow dots are all locations of those crashes, the serious and fatal injury crashes. What does it sort of look like to you where those dots align? So they're primarily on major streets, right? And so that's one of the reasons why we want to study the effectiveness of different engineering design treatments for crossing the road. This particular research looked at the effectiveness at mid-block crossings. So these are crossings not at intersections, not at signalized intersections. So crossings in between signalized intersections. And we wanted to estimate in the safety literature a factor that's called a crash modification factor. It's basically an estimate on the reduction in the number, or the change in the number of crashes, where 1 is no change, anything over 1 is an increase, and anything below 1 is a decrease. So those are our objectives. The project was funded by the Oregon Department of Transportation. So just some examples of some mid-block crossings. These are all from Google Street View image that I captured. Not all of these were ones that were selected that were in the study, but the one on the top is sort of kind of a bare bones, right? Mid-block crossing. The striping is a little worn out, but that's sort of the basic mid-block crossing would be the crosswalk lines extending across. This is in Eastern Oregon. You can do a lot more at pedestrian crossings, and this one shows one here on Barber with enhanced continental markings, a median refuge, dual pedestrian sides, and a stop ahead, a stop here for pedestrians, so a stop ahead for pedestrian stop bar. So that's an enhanced crossing. These are two pictures of what are a relatively useful tool that's just kind of come online called an addition of it's a rectangular rapid flash beacon, and I'm going to abbreviate that RRFB in the crossings. You can see this is also similar sort of advanced stop bar, stop here for ped signs, the continental markings, the refuge median, and then the two ped signs. What's different is but you can't see it on the photo, is that here there are these two high intensity LED beacons that flash in a staccato pattern. They're activated by the pedestrian when they push the button, and then they stay active while the pedestrian is crossing is exposed in the crosswalk area. This one is on a little lower volume road, a little bit, it just has the enhanced longitudinal markings, the pedestrian signs. And then these are RFBs. Interestingly, you can still sort of see there used to be in pavement warning lights here. I sort of know this because I had walked over this crosswalk many times. Nobody's using those in pavement crossing lights anymore. They prove to be sort of not very effective. Kind of moving up, there are also crossings, and these beacons can be placed overhead. This is a fairly significant investment in the beacons. These sort of predate the RRFB applications. I think primarily now, if they want to add active warning, they will use the RRFB instead of the beacons. But there still are a lot of installations where there's some sort of yellow flash beacon. They don't flash as bright, and they're sort of sometimes just they'll just blink when the pedestrian activates. So those are yellow. The sort of the highest level of treatment besides a traffic signal would be a pedestrian hybrid beacon, and this is in this application here. These are stop condition. So the pedestrian pushes the button. It rests in dark. It comes on, and then it starts flashing red. So the idea is that vehicles will stop, but it's flashing red. So what that means is once the pedestrian clears the crosswalk, the vehicles can go. The full traffic signal right at a mid-block location are relatively rare because the warrants for a mid-block crossing demand relatively high pedestrian volumes, and it's very difficult to install a full traffic signal at a mid-block location. All of these crossing locations would not meet the warrants for a full traffic signal. So the pedestrian hybrid beacon is kind of the one that gets the stop condition for the vehicles. It also is the one where drivers don't always understand what they're supposed to do. Many times they'll wait for even when the red flash is still going and there's no pedestrians, they won't understand that they can proceed. It's a device that used to be called the Hawk signal, and it started in Tucson, Arizona. So all of this sort of pedestrian crosswalk marking work sort of anchored in some work that Charlie Zagier did in the early 2000s, where they looked at a fairly large sample of marked and unmarked crosswalks at unsignalized intersections. And after controlling for pedestrian volumes and many other things, their basic conclusion was that if you have a multi-lane roadway and the traffic volume is more than 12,000, just putting down markings without any enhancements, such as the refuge or beacons or advanced stop bars, is actually worse than doing nothing at all. And so since this study has come out a long while ago, the many sort of pedestrian enhancement type approaches is the standard. So that crosswalk that I showed you with just the striping with nothing else, on higher volume roads, it will be very challenged to sort of find those. That's why I had to go to Eastern Oregon, to some small town, to find a picture of one. So, of course, lots of other people have sort of looked at what the effectiveness of these different treatments are. You'll see as I kind of go through my talk that it's one of the challenges with estimating safety related to pedestrian crashes is that there's not very many of them, so that's a good thing, but it also makes a lot of statistical methods challenging. And so in this table, there's a clearinghouse that the Federal Highway Administration provides. It's called the Crash Modification Factors Clearinghouse. They rate things on a 1 to 5 star rating, sort of like a Yelp for traffic engineers, for traffic safety engineers. 5 stars would be the best. It's related to study quality, sample size, things like that. And so those are you can see there's not a whole lot of pedestrian engineering design treatments with 5 star ratings. Most of them are 2 or 3 star ratings. These are the ones with the 1 subscript. Those all refer to just pedestrian crash types. So, so for example, installing a raised median with a marked crosswalk where there wasn't one estimates a 50%, this 0.54, roughly a 50% reduction in pedestrian crashes. The other one to note here is the pedestrian hybrid beacon. This study estimated a 0.31 crash modification factor, so roughly a 70% reduction in pedestrian crashes. That's the refuge where you can wait in the middle. Yeah, yeah. Yeah, there's a link at the end. There's a report that this is from where I sort of summarized all that. Those data are from the FHWA's crash modification factor clearinghouse website. If you just Google that, it'll come up. There is some new work that was sort of going on at the same time that ours was being completed from the National Cooperative Highway Research Program. It's called 841. They looked at pedestrian hybrid beacons, RRFBs, pedestrian refuge islands, and those advanced yield and stop markings. And you can see the estimates of their safety effectiveness estimates that they found, with the hybrid beacons having sort of the most effect on pedestrian crashes. This study, they haven't yet rated it with the star ratings, but it will probably be 4 or 5 star ratings when they had a significant budget. They collected pedestrian volumes. They had a large sample size, so it meets all the criteria for that. So just remember that sort of RRFB CMF, because that's, in the end, that's all we were able to sort of estimate out of our data was a CMF for RRFBs. They got it at 50%. So our study sort of looked at statewide crossings. You'll see a map in a minute. We had 191 crossings in sort of what we called the high visibility, flashing amber, or RFB categories. There's just not enough pedestrian hybrid beacons in Oregon. There's less. At the time we did this study, there was probably less than 10. There may be more. One of the challenges with doing this kind of work is that if it's not on the state highway system, it's very challenging to sort of find out where these locations are. We did a lot of calling to city traffic engineers, trying to find out where they're at. We did a lot of looking on Google Street View to sort of look at locations. The inventory of where crossings are, besides the city of Portland, which sent us their GIS database, some of the smaller cities don't have very accessible records. So, and one of the things that in order to estimate how effective something was, you need to know when it was installed. And a lot of times that information wasn't available. So that really sort of, our initial pool of things that we were looking at was much larger than 191. But as we sort of were unable to sort of establish when when the location was installed, we had to drop it from the sample. So like I said, fairly good coverage around the state. You can see, if you're familiar with the geography of Oregon, that the urban areas are where these crossings are, especially the RRFB crossings. The standard crossings, which are those yellow pins, or the high visibility crossings, tend to be into smaller, the lower volume locations. Okay, so roadways are sort of divided up by who owns them. So the state owns some roads, the county owns some roads, the city owns some roads. The state highway system has a fairly robust data collection system and inventory system. And as part of their data collection activities, they do the Google Street View of all the state highways in this. Not all, most of the state highways in the state. They do all roads on like a 2-year cycle. But they've got a catalog where you can go back as far as you want, which is what you can do a little bit on Google Street View. Depends on how often the Google car goes. Sometimes in Portland you can find 3 or 4 time periods. It's not consistent. It's sort of, you're at the whim of sort of when Google decides to re-Street View things. And in some rural areas, they just don't ever go back, and so you don't get this time series. So locations that were on the state highway system give us this advantage of being able to see when things were installed, even if there isn't a record. And we can also see how the crosswalk changes over time, which was something that was very challenging to account for in the research, in that a lot of times there's very few locations where they just kind of come in with everything, the wholesale treatment. If it's a new installation, you'll kind of get things. But if it's been an existing crosswalk, you'll sort of get this piecemeal enhancement where perhaps it's, it looks like this one here where it's just the standard marking. Then you'll get the longitudinal, then you'll get the RFB, then you'll get a median, then you'll get a beacon. So it gets added on, and without careful accounting of when that particular time frame happened, it's very difficult to do the before-after safety evaluation. So we were very careful about what the location, what type of enhancement was present at the location for each time period. So just at the end of the study, we got access to 2015 crash data, but we left the crossing inventory was through 2014. And you can see the red bars are the RRFB installations, and you can see that most of those are relatively 2010 and forward, and becoming a greater share of the crossing type. This is just the raw count of the 191 crossings. You can see that some of the crossings were unmarked and then became marked. But you can also see that some of the crossings moved up basically in the enhancement style. This graph shows that a little bit better. It's a little hard to sort of look at, but it sort of visually shows you any one line, any one vertical column. You can see up at the top the crossing ID numbers from the data record. The shading is the same as it was before, but you can look at any one crossing and see how it changed over time. So, for example, this crossing was unmarked, and then it got the RFB enhancement. But see if there's any ones that sort of change a little bit. So this, this one was unmarked, then it got the flashing amber, then it became RFB. And it's from 2007 up at the top to 2014. So this is kind of a visual way to sort of look at these. It's not a static engineering treatment at these locations. They often change, either as more tools become available or pedestrian volumes change, and that warrants additional treatment. So part of our challenge in doing the data analysis is when we're trying to compare, what's the safety of an RRFB from the before to after condition, we have to be very careful about what the before condition is and what the after condition is, and how long it was in each of those particular categories. Safety, crash data is strongly correlated with exposure, and by exposure I mean both motor vehicle and pedestrian traffic, right? So you can't have a crash if there's nobody there. So you need cars and you need pedestrians in order for a crash to occur. The motor vehicle volume is very easy to obtain, and even if you can't get it at that location, you can get it, down the street somewhere, and there's lots of factoring methods, and so it's never a very difficult problem. It's sometimes you got to do a little bit of hunting, but it's it's not hard to find the average daily traffic, so the vehicle exposure. On the pedestrian side, there's virtually no systematic counts, so there's no way to sort of estimate the exposure at any one of these locations. One of the challenges about these enhancements is that the hypothesis is obviously that if the enhancement is increased, it may draw additional traffic to it. So if you see additional pedestrian traffic to that particular crossing, so there could be more crashes because there's more pedestrians, not necessarily because there's anything different about the design. So accounting for the pedestrian volume is fairly important. We didn't have the budget to do any counting, and there wasn't any counts available. So we tried to capture this by sort of general land use characterization and counting somewhat what are known traffic generators for pedestrians, the presence of them, which you'll see in the next couple slides. So you don't have to dig into the table too much other than to sort of see down the left side what are some of the elements that we collected at each crossing. It included sort of the usual things like how many lanes, what was the posted speed, was there bikes or sidewalks, was there bus stops because transit activity is a pedestrian generator, was there a school, was there some other engineering features, curb ramps, light poles. So those were continuous variables we collected, the number of things, and then we collected a lot of sort of binary sort of yes, no, presence of things. So all of those different marking types I talked about, yield aheads, raised median, refuge island, school signs, presence of school, shopping center within I think it was 1,000 feet, bus stop, things like that. So we collected all the engineering details so we could make some comparisons between them. We collected a lot of the generator data so that we could categorize the pedestrian activity level. And so we spent a lot of time sort of looking at how this might work. We looked at using walk score as a way to sort of characterize the walkability and include that in our sort of characterization of the potential pedestrian activity level. But in the end, we sort of came down with this table. We basically characterized pedestrian activity from very low to high, isolated. We had two sort of, kind of an isolated rural or a major urban center or near urban, like a suburban setting. And we used the presence of bus stops, shopping centers, and schools as a way to categorize the potential pedestrian activity. So when you're looking at the reported crash data, you also have to be sort of fairly selective about which things get put into your hopper for evaluation. And so for the pedestrian crashes, we initially sort of used a fairly large buffer of 500 feet around the crosswalk. All the crashes are geolocated with lat longs, and so you can do some fairly precision analysis, even though the reporting and the location of crashes isn't all that precise. That's why we use a buffer. We went down to 300 feet, and then we went to basically each of the 191 crossings, and we sort of looked at each of the pedestrian crashes that were potential to be included and decided if it was related to the mid-block crossing or not. So this one shows a nice geometry where that's the mid-block crossings in the middle. There's no there's no other sort of there are adjacent streets, but there isn't a signalized intersection nearby and things like that. So at some locations, the mid-block crossing, the buffer you would draw, there would be crashes that would be in that buffer that shouldn't be part of your evaluation of the mid-block crossing. So we did a careful sort of sifting through of all the pedestrian crashes. And here's kind of here's a distance of those pedestrian crashes, about how far they were from the crosswalk, from the center, measured from the center of the crosswalk. And it was about 75 feet that we ended up selecting things on the inside. So most of those ones that were farther away, we determined were not related to the mid-block crossing. So I've been mainly talking about pedestrian crashes, but the other crash type, a full safety evaluation should sort of look at what might be the effect on all crashes. And for the installation of an enhanced pedestrian crossing, there might be a change in rear-end crashes. If there's more pedestrians, or the enhancement makes the pedestrians more noticeable, which is what you want, you might get more rear-end crashes. And so we looked at rear-end crashes. You can see the difference between the two charts at these locations about how many more motor vehicle crashes there are. We just used a 75-foot buffer as counting those crashes related to the mid-block crosswalk as rear-end crashes to look at. So our analysis sort of looked at the pedestrian and the crash and the rear-end crash data in sort of the same format. I'm going to kind of walk you through that. We kind of looked at some descriptive statistics and some ways to sort of compare some of the data we collected, and then did four methodological attempts at estimating these crash modification factors. So it's hard to show things in frequencies because of the differing time periods of these installations in the before to after period. So they weren't consistent, in terms of when installations were in. But you can look at basically the percentage of these different crash severity types. Fatal crash is sort of self-explanatory, but an injury A crash is a severe crash that essentially means that somebody had to be transported from the scene in an ambulance. And the B and C injuries are moderate and minor injuries. And so you can see the dark blue is the before and the light blue is the after, and these are the proportions of those, the total crashes that happened in the before and the after period. You can see that there's a shift in the sort of the severity proportions after the enhancements. So there were fewer percentage of fatal crashes and fewer injury crashes, fewer percentage of the severe injury crashes for the pedestrian crash distributions. Now for the rear-end crashes, and rear-end crashes are very common, but they're not generally very severe. So there's no fatal crashes. I think there's one injury A crash, but the severity distribution of these crashes didn't, the proportions of those didn't change for the rear-end crash types. So you want to look at, when you're making treatments, you want to look at sort of the severity changes or the effects of those. It's important in the safety consideration. You might think of like putting up a barrier between two travel, down the middle of a freeway. It basically eliminates head-on crashes, so it gets rid of, has a really significant effect on really severe crashes. But now you put a barrier there that people can hit, and so property damage, sideswipe crashes tend to go up. But it's a severity trade-off that we're willing to make because we'd rather get rid of the severe crashes and have a bunch of minor crashes. And so I'm not looking at rear-end crashes because I'm trying to make it. I'm not saying that they're obviously the pedestrian crash is the focus of the enhancement, but we should look at what happens on the rear end side. And I don't expect to see much change in the rear end crashes. And so when I don't see that in the data and my methods sort of go along, it gives me a little bit more, another data point to sort of see how the methods were working. Again, because of the differing time periods of when things and the transitions from one type of pedestrian crash enhancement to another, we did this sort of calculation of what we called a risk ratio. And you'll see, and we did it for a lot of the variables, but I'm going to only show you for a couple of them. So basically what we did is, like for some of those ones where it's like number of lanes, 2, 3, 4, 5 lanes, these are the number of observation years, right? So if the location was in a 2-lane situation and it was always flash for 5 years, that would be 5 observation years. So we totaled up what are the number of observation years for each of the configuration types for the different, so for things down the left column. And then we put the crash counts in there, right? So So put the crash counts, the pedestrian crash counts in those. And then we basically said, well, what's the percentage? It's just a simple ratio of the percent of the crashes in that particular column versus the percent of observations in that column. So the percent of observation years in that. And so you get a fairly consistent picture. I don't know if you can compare the risk ratios between the different categories. And for me, that doesn't necessarily mean anything. But if I look at sort of the trend between those, the dark blue is on the left side. The dark blue is, this is five lanes, and this is 2 lanes. And you can see the trend in the risk ratios. That goes down for the number of lanes is consistent across all crossings. And that aligns with what the literature shows, and probably from your own perception that the fewer lanes you have to cross, the safer, the less likely that you're going to get involved in a crash. It's the same trend also held for speed, so the posted speed. So the top bar is the 45 miles an hour, and the bottom bar is 25 miles an hour, and you can see how the risk ratios declines consistently for each of the categories, for each of the in the speed pattern. So we did a few more of these. We tried the land use one, or the pedestrian activity one. Doesn't look as pretty as these, and a few of the other ones don't kind of have interesting patterns. But it was good to sort of see these 2 things, which is in the data, which is what the literature sort of suggests, that those 2 things are sort of key risk factors on the pedestrian side. We did, so kind of digging into the meat of the safety evaluation methods. You can, from the left to the right, there are 4 different methodological approaches. There's actually one more after this empirical Bayes approach called a full Bayes approach. The simple before-after, most of the things that sort of get 1 or 2 star ratings, they just use the simple before-after approach. It doesn't allow you to basically control for selection bias or, in our case as well, exposure changes. Another approach you can take is because what you're trying to do in safety evaluation is, if you've got a location in a before condition, you know the counts of crashes that happened then, and then you know the counts of crashes that happened afterwards. But what you have to predict is what would the crashes have been had there not been any treatment. And these 4 methods are different ways that you can estimate that. So the simple method basically says, if I had 2 crashes per year before I did the treatment, I get 2 crashes per year after I did the treatment. The comparison group says, well, let me find some other locations that have similar things about them. Let's look at how the pattern of crashes changed from before to after, and use that ratio as saying how I'll change, what the crash count would have been at the treated location. The cross-sectional analysis is a totally different approach. This is a regression modeling approach where you put all the treated and non-treated locations in a regression model, and you look at the effect of the treatment from a regression coefficient. Now, there's lots of debate about whether extracting the regression coefficient for safety effectiveness is reasonable, but we did it anyways to sort of see how it sort of lined up. The best approach is this empirical Bayes approach. It allows you to sort of control better for changes in exposure and also selection bias. It requires that you are able to estimate what's called the safety performance function. It's a log linear prediction of the crashes as a function of exposure, basically. So the 2 on the pedestrian side, we did the cross-sectional analysis, but nothing came out as significant, and we didn't have any pedestrian volume, so we weren't able to estimate performance function, so we couldn't do the EB approach there. But on the rear end ones, we were able to sort of do all 4 of them. So let me kind of walk you through the results. So here's the pedestrian crashes. This is the simple before-after by the different pedestrian crossing enhancements. And one of the things that's the clear limitation and why we sort of dropped off the flash and high visibility locations from sort of any recommendations or conclusions is that there was just very few of those locations. So we had 19 RRFB locations, but only 3 flash and 5 high visibility locations. We finished the work with 2014 data, and then we got 2015 data. And because these counts are so small, having one more year's worth of data is very useful. And so we re-estimated those with the 15 data. It's also good if you see wild swings by adding 1 year of data is another clue that things aren't that good in the data you have. So the RRFB location, I've highlighted the most important row is the CMF. We want those to be less than 1. For the RRFB, with the 14 data, we had a 20% reduction, and then with the 15 data, it went down to about 40%. You can see the flash estimate is relatively unreliable, and the high visibility locations actually the method sort of forecast an increase in pedestrian crashes, but again, we don't also consider it very reliable. I'm not supposed to point at the screen. With the methods here, you can sort of estimate the standard deviation, plus or minus 1 standard deviation. And so the addition of more data years and larger sample size allows you to get a more precise estimate. And so at least in this, with 1 standard deviation, we don't overlap 1. If you overlap 1, that means the treatment sometimes the treatment works, and sometimes it increases crashes, or at least the confidence interval in that. But if we go all the way out to the 95th% confidence interval, our estimate still overlaps the bounds. So, but at least at 1 standard deviation, it's below 1. So. I mentioned, the cross-sectional approach is to estimate the regression model. It had all the variables in it. We tried to squeak as much information as we could out from the data, but the only thing that came out significant was the motor vehicle volume, and not the presence of the treatment. So then we weren't able to estimate a CMF from the cross-sectional approach for the pedestrian model. Looking at the rear end crashes, again, the small sample size on the flash and the high visibility locations sort of resulted in sort of the CMFs that are not, the confidence interval is too wide, and we're not really recommending those for use. But for the RRFBs, we did see a slight, an increase in the rear end crashes. But this is with the simple method, so 1.3. It did come out in the cross-sectional analysis, so you can see the treatment is a significant variable in the model, and you just take that coefficient and you exponentiate it, and you get the CMF, so 1.75 CMF using the cross-sectional approach. Because we had motor vehicle volume, and that's usually explains about 80 to 90% of the variation in motor vehicle crashes, we were able to estimate this SPF, a safety performance function for rear end crashes. So that's the log linear model up at the top. It passed sort of all the basic diagnostics that you do for these negative binomial models. And then you run it through a very similar procedure as the simple before-after, but the counts are adjusted in a different way. It's adjusted using the model. The model on the top basically predicts the number of crashes based on the exposure at that location, and then you can do a better job of sort of forecasting what the crashes might have been. It allows you to get a more precise estimate with less data. It's more efficient. So the CMF for the rear end crashes with the better model and the better approach is 0.93, so essentially no change in rear end crashes. So kind of looking at it across the spectrum, just for the RRFBs, because that's what we sort of zeroed in as it's also what the technical advisory committee sort of was most interested in finding out what the result was. And I didn't show all of the different analysis to sort of keep you from falling asleep. But we sort of recommend, because that was the only one we had, is using the simple before-after approach, the CMF from that. If you remember back to the NCHRP study, it was 0.56, I think. And what happens generally is the more things you control for in these, as the model, as the safety effectiveness methodology improves, you get a better estimate. And so it compares fairly well to the NCHRP CMF, given all of the uncertainties in the pedestrian crash. Their sample was nationwide, and Oregon does have some particular crash reporting thresholds that make it a little bit different than other states in terms of the number of crashes that make it into the database. But we feel fairly confident in that CMF for RFBs. We've got a follow-up study that's looking at a little bit more detail on some design iteration or design approaches for RFB locations at 3-lane crossings, about whether the presence of the median changes yielding behavior. And we're also going to collect enough pedestrian estimation, enough pedestrian counts to
hopefully develop some pedestrian estimation models, and then we'll be able to sort of re-estimate this with an SPF. And probably another 2 years worth of data. So we should have a better and more precise estimate in a year or two. On the rear end crashes, it does sort of, you can kind of see that progression, at least from the simple to the before. The more things we controlled for, it got closer to our sort of expectation of having not really any change on the rear end crashes. So, in the cross-sectional analysis, we did it, but because of the only way that you can do it is you need the consistent time period between when things were, when something was was treated and then not treated, and it was very, in terms of sifting through the data to find a sample large enough to estimate, it was very, there wasn't a lot there. So, and the same thing with the comparison group. Those two approaches, the methods based on the number of data we had, were, I didn't have a lot of hope in them kind of working, but we tried them anyways. So I think I've sort of already mentioned a lot of the sort of the challenges with the data. No consistent logging of installation dates and minor modifications is a particular challenge when you're trying to dig into the details of these engineering modifications. We do have there's a former PSU student that works at Oregon DOT's in the bicycle and pedestrian program, and he's got a great spreadsheet where whenever he hears about some of these enhanced crossings, RFBs or pedestrian high-beam beacons, he gets the installation details. So it was a super resource that allowed us to have a lot of detail. It's not part of their regular data collection, but he does keep track of a lot of the installations. So we do have some next steps that I mentioned. We're going to have a follow-on in this project, looking primarily at sort of whether the refuge median island with the RFB is required in terms to get the yielding behavior. So you have the median refuge. You also get the opportunity to place a second sign. So you saw a lot of those, how you get the two signs and the two beacon. If you have the RFBs, then you can have it on the left and the right side of the road. If you don't have the refuge median, then you can't put a signpost in the middle, and then you only have the RFB on the right side. So we're going to be looking at that in a little bit more detail, and then as I mentioned, trying to estimate some PED volumes. So as I mentioned, it was funded by the Oregon DOT. This is the State Planning and Research Project 778. My co-PI was Miguel Filiozzi and Sarisha Kothuri, a research associate, and the two students on the project were Ali Razma and Dan Hazel. And then the picture on the right just is a warning for you if you come on any
trips with me, you are likely to have to pose in pedestrian crossing pictures, because so that's my my sister's wife and her husband. When we were in Sisters, I said, "Oh, pedestrian flags! Can you show me how those? I need some photos." So, so anyways, it's a warning. If you come with me, you might show up in a photo. So, okay. So, if you're online and you're emailing questions to psuseminar.yahoo.com, unfortunately, I didn't bring my laptop, so I'm not going to be able to respond to those. But if you're, what's that? It's fine. When there's only one of us, it's hard to sort of handle the online questions. But in the room, let's have some questions. So, and just remember that I'm not going to be able to log your questions, so just come up afterwards to make sure that your question gets logged. So I'll start, Travis.
In the slide that was showing when each of the different safety features was installed, none of them didn't have anything at the end.
Right.
Were there any control groups that you looked at, or ones that saw no improvement at all?
So remember the map that had the standard all the little yellow pins, the standard crossings? That was our original intent, was to use those. So just the standard crosswalk markings with no enhancements as a control group. It turns out there's almost no pedestrian crashes at those things. So it was essentially useless from a statistical sense to use them as a comparison group. So that's why we initially had identified a lot more. I think it was like 397 crossings that we were going to look at. But when we looked at the crash data at the standard markings, and this is often what happens in safety evaluations, is that it's not like medical research where you can have placebo or sort of controlled study. The transportation agencies only invest things where they need to be, and so you often also get selection bias in that they just don't put out a mid-block crossing and do all the bells and whistle at a place where they don't have any problems or there's a hard crossing. And so that's why the other methods also do a better job of sort of controlling for that selection bias. So yeah, we tried to do some comparison. We tried to have a control group, but no such luck.
We'll guess. The time of day of the accidents in your data set?
Yeah, I had another chart. Sort of, we had time of day and month of the year that did shift with the enhancements. A little hard to sort of tease that out, but especially the time of year shifted, and that could be related to the visibility of the enhanced locations, and there was some time of day differences, but it wasn't. It was observable, but not that pronounced. Yeah, the crash data reports crashes in hour bins. So, so John, and then.
So the enhanced treatments are generally where you have accidents. The reason for the question, so on 4th, since I was in the Market Center building for 6 years, and it was kind of terrifying to cross there at like all the time, especially rush hour. And it's pretty minimal signage there.
Yeah.
It's just a sign. There's nothing flashing. How expensive would it be to put one of those blinkers on there?
The RRFB things are relatively inexpensive. It's probably the whole package is sort of probably less than 10,000. In the downtown core where you've got the signals, that's usually and striping of the crosswalks is a I guess is a challenge for PBOT on when to stripe them and then when to add those enhanced.
What's your impression as a pedestrian expert?
I don't cross at the Market one, just because the vehicles are on a downgrade. They've just been discharged from the upstream signal, and so they're always going a little bit faster there than they are. The one in front of the engineering building with the double marked crosswalks, I tend to feel a little bit better about that one. And Dr. Filiozzi's done a lot more work on that one in terms of the yielding. And we did actually, when they've done this construction at the 4th and Harrison block, we did have some inquiries with PBOT about how they're shifting the traffic, all the PEDs over to the one side, making us cross twice. But now that you see the construction at that building, there's really no accommodation they could have made for pedestrians. So but you can walk in the super blocks, which is what I do now to get to Market Center from engineering. So, yeah.
When a road has an ADT of more than 12,000 mid-block crosswalk, it's not that helpful.
Yeah.
It's actually worse.
Yeah.
Do you think that's because maybe there's more lanes on those roads, or like higher speed, or like could you like pinpoint?
So
that recommendation is specifically referring to a marked crosswalk with no enhancements. So that's kind of like that first one, just painting the two lines, or painting the longitudinal bar lines, the continental crosswalk markings. If it's 5 lanes and there's that much traffic, just painting the lines isn't enough, is basically what the conclusion was. That you need to, at the very minimum, provide a refuge island and probably some additional signage and beacons. It's one of these things where the literature will sort of, and other people will sort of say it gives pedestrians a false sense of security. I'm not always a fan of that particular terminology, but you can see what they mean in that if you're a pedestrian and you're looking at the crosswalk, especially if it's the Continental Ladder, you see this like path for you. What you don't realize is that the drivers don't see the same path to you. The markings are in a different sense, and there's no other clue other than you that you're about to cross this very busy road. And if it's 5 lanes, that means you've got to find a gap where you can get all the way across. And so, it makes a lot of sense, the recommendation. Some people will sort of extract that sort of false sense of security idea and say we should never mark crosswalks. I don't think that's the case. At least in many of the cities in Oregon have a very pedestrian-friendly, forward view, and that they would prefer to mark things where their pedestrians are crossing. But in many other jurisdictions, they will sort of say, well, if I mark it, it's worse than not marking it, so I'm just not going to do anything. I don't think that's the correct approach either. I think if you have pedestrian demands and they need to get across the road and you can't provide them with a signal, then you should provide the sufficient enhancements so that they get the yielding behavior so they can get across the road. But behind you, Travis, before. And then come.
Mr. Keller, so you were mentioning how the traffic density, the pedestrian traffic density, is a big factor in determining whether or not they're going to implement an enhanced crossing. What is kind of like the threshold for that propels them to actually take the steps to do that?
There are some numbers, I can't remember them off the top of my head. It's oftentimes not necessarily driven by just that. I mentioned the numbers. So you want to put up a full traffic signal. So you want to put up a traffic signal in the middle of the road that just stops cars so pedestrians can get across. You probably noticed you don't see very many of those. That requires some ridiculous number of pedestrian per hour that you really only see in sort of downtown type cores, right? And so you won't see a full stop of traffic with a signal because the federal manual that allows the warrants for traffic signal has set the bar so high. They will allow the pedestrian hybrid beacon and which does stop traffic at a lower volume. It's hard to sort of justify the difference between those two, other than that when the pedestrian is done with the red flash, the vehicles can discharge. But the literature has shown, the reviews, a full stop situation is sort of the best for providing a safe crossing. If you have a really long crossing and you do the red, yellow, green timing, the timing to get the pedestrian all the way across is very long, and so that basically is a lot of times the deciding factor about whether to signalize things. So yeah, there are numbers. I think that it's like 400 an hour. I think for the PED signal. If I might be incorrect there. Okay, Travis.
Is there evidence that compliance goes down as more of these are installed?
So the only research that I've seen is by Ron Van Houten. He's at Western Michigan in the psychology department. He has done a lot of sort of work looking at the time effect of basically drivers' yielding behavior relative to sort of the novelty of the treatment. And I think they're I can't recall exactly the results of that. The other part of your question is, if we put more of them up, are people just going to not pay attention to them? I don't know. I think the RRFBs are a pretty useful tool in that it does indicate that there's a pedestrian waiting to cross. I think the implication might be if you had a corridor where you had like 5 of those, and then there was a PED at every one of those, then drivers might start to go, they might start to feel and have less than ideal performance. So I think the spacing of where you put these crossings in is important, but I don't know if using them, like lots of RRFBs, is going to change the yielding behavior. I think it's a fairly well understood traffic control device. The yielding behaviors at some of them in Oregon are well over 90%, close to 100 in some locations. Even in Florida, it's over 90.
Oh, I saw that you looked at pedestrian and rear end crash data.
Yeah.
Are there any other types of crash data that you can have?
No, I mean, we're sort of sifting through the types of crashes that would be affected by the treatment. Those are the 2 that we focused in on. So, I mean, you could also look at total crashes. At a mid-block crossing like that's probably 95% of the crashes that you have. There'd be bike crashes, but there wouldn't be very many of those. And then you wouldn't have, because it's mid-block, you wouldn't have any other vehicle-type crashes, except maybe sideswipe-type crashes. But we didn't look at those. All right, so it looks like we're close to 1, so that will be the last question. Thanks for your questions. Make sure you signed in the sign-in sheet, and then log your question back there. And if you didn't, write one out, and I'll get it recorded. So thank you.